Welcome to Honors Algebra 2 Pre-Calculus Hybrid course. In section 2.3, this is a biggie. This section really should be called the hunt for zeros. And one of the things we're going to learn is synthetic division. Typically this is taught in Honors Algebra 2, so we're going to have to be pretty quick on the uptake on this. I'm just going to give you kind of an example of the process of synthetic division. I'm going to steal the coefficients. From this, I have ax to the fourths and bx cubes and cx squareds. Let's say I had no x squareds. I'd put 0 here. But I have c of them. I have dx's. And if I didn't have a constant at the end, I would still put 0 here. But I've got e at the end. And then I'm going to synthetically divide x through this. And this is going to help explain a rule we're going to learn later on a remainder theorem from synthetic division. But anyway, when I set up like this, the very first thing I do is I take this number, this coefficient, and I just bring it down here. And then I multiply these two together and put that product up here. Next, I add down, so I get ax plus b, and then I just multiply in. So distribute x in, or ax squared plus bx, add down, ax squared plus bx plus c, multiply x into that result, distribute it through, ax cubed plus bx squared plus cx, add down, ax cubed plus bx squared plus cx plus the d, multiply in x, I think you see where we're headed here, I get ax to the fourth plus bx cubed plus cx squared plus dx, add down, add the e into there, and I end up with ax to the fourth plus bx cubed plus cx squared plus dx plus e. And I end up with this, and that's going to help explain one of the things that synthetic division does for us. And you'll see some more examples of synthetic division as we go forward. This is really just kind of a review normally, but it's just an introduction to synthetic division. But this isn't synthetic division, this is plain old division. And we did this type of problem in our mechanical kind of qualifier test, our algebra mechanics quiz that we had earlier. Some of you are still working on getting through that, but it's gone well. I'm going to set this up just like a division problem. We know what we're doing here, 2x minus 3 into. Now note, if I had no x squareds here, it just went 2x cubed minus 50x, I would write plus 0 x squareds here. But I've got x squareds, and I've got x's, and I've got a constant. So my next question for myself is, what do I have to multiply 2x by to get 2x cubed? Since that is x squared, I'm going to put it above the x squareds. And that gives me distribute 2x cubed minus 3 times x squared minus 3x squared. And in division, after we do that multiplication, we subtract. So minus, and this minus would become plus. This is 0, it better be, that's why we did it. This is 0, that's kind of a coincidence. So let's see what happens. I don't have to find out how many times 2x goes into 0. How many times does 2x go into negative 50x? Plus 25. Just plain old 25. I'm going to put that in my plain old column. Oh, minus. Sorry. Minus 25 because it's negative 50. So I get minus 50x, but I also have to multiply minus 25 times minus 3. I get plus 75. So I'm going to bring this 75 down. And we are to subtract those. So this becomes plus, this becomes minus, and I end up with no remainder here. So my solution is just x squared minus 25. But what that really tells me, if I take this kind of preface for the next problems, is that this guy has a factor, because it worked out evenly, of 2x minus 3, and another factor of x squared minus 25, but hopefully we all identify that as a perfect square minus perfect square, x plus 5 times x minus 5. So this is equal to that. But our solution for this problem, because all they asked was the division, is right here. Okay, now synthetic division. When the lead coefficient of the number I'm dividing by is 1, we can synthetically divide. I'm going to set this up as 5x cubes, 0x squareds, 6x's, and an 8. And what we synthetically divide into this is the MyVox, -2. -2 is what would make this 0, our most interesting value of x. Here's the process. We can get really quick at this too. I bring down the 5, I multiply, 0 plus -10, -10, -2 times -10, 20, 6 plus 20, 26, times -2, -52, and 8 and -52 is -44. Here's how we interpret, a lot of people will put a line right there. Here's how we interpret that. 5x cubed plus 6x plus 8 divided by x plus 2 is equal to, if this was an x cubed, this becomes an x squared, etc. So I get 5x squared minus 10x plus 26, and our remainder is minus 44, and that is yet to be divided by x plus 2. And might be a nice time to just pause and try this with standard long division and see if you don't come up with that same thing. I think when the lead coefficient is 1, and that's when we can synthetically divide, this is a really, really good alternative. Okay, number 32. This is kind of a weird problem. I'm going to set this up. Let's say we just had 49 divided by 8. So I go 8 into 49. It goes in 6 times 48 with a remainder of 1. And we might write that's 6 and 1/8, or we might say it's 6 with a remainder of 1. Okay, here's what they're trying to get us to do here. Write the function in the form of f of x equals x minus q times q of x plus r of x. R is our remainder. Q of x, well, let me show you this first. Is it clear here then? I could write 49 equals 8 times 6 plus 1. All my pieces here. Okay, so 8 is what I was dividing by. 6 is the answer I get, plus 1 is the remainder. This is like dividing by x minus k, basically. That's what we're doing here. So I'm going to, so that's x minus k. K is negative root 5. Notice that would make this x plus root 5, and my MyVox is negative root 5. This seems like it's going to be messy synthetically. 1, 2, negative 5, negative 4. But let's see what happens here. How bad can it get? Bring down 1, multiply by negative root 5. Add these, I get a 2 plus a negative, or 2 minus root 5. Multiply by negative root 5. Negative root 5 times 2 is negative 2 root 5. Negative times negative is positive. Root 5 times root 5 is plus 5. So that's not so bad. In fact, it just got better. When I add these, my 5's cancel, and I get negative 2 root 5. 5's cancel. Times negative root 5. Negative times negative positive. Root 5 times root 5, 5 times 2, 10. And I'm left with a remainder of 6. So what I divided by, x plus root 5, that's basically what I was dividing into this, x minus my k value. What I ended up getting, well, this is kind of weird. This is an x cubed, so this would be my x squared. I get an x squared plus a 2 minus root 5 that gets multiplied by x, another minus 2 root 5, and what's my remainder? My remainder is 6. So I'm led to believe then, if I superfoiled, distributed all of this out, and added 6 back in, we would get back to there. there is not a great mathematical purpose for doing this other than kind of tying in this correlation of what's going on right here. So really it's just kind of algebra gymnastics. Now, what the remainder theorem says is, this is pretty cool, and this is what I was really trying to illustrate there. Let's say I put 2 in. If I put 2 in here and ran x through all of this, notice by the time I got to here, I would have a times 2 to the 4th, and b times 2 to the 3rd. And whatever value of a is, whatever I'm left with here in the remainder position is what f of 2 would be. And you say, well, why wouldn't I just put the 2 in here, take it to the 4th, take it to the 3rd, take it to the 2nd? I think you'll be sold on this after we go through an example or two. So I'm going to set this up for synthetic. It's going to be 2. I have no to the 5th. I've got to account for that. Then a 3x to the 4th. I have no x to the 3rds. I have to account for that. Then I have negative 1x squared. I have no x's. I have to account for that. And then I have a 3. And I'm going to synthetically divide through this 2. And supposedly what I get here in the remainder is going to be my solution. Let's see here. Now the zeros definitely help. But let's watch this process. Bring down the 2, multiply by 2, add them. 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 Multiply by 2, and end up with 175. You're like, well, that wasn't so easy. Well, then do this. Take 2 to the 6th, figure out what that is. Take 2 to the 4th, figure out what that is. Multiply by 3. I'm not so sure this isn't a pretty viable option. Let's set this up for 3. 2, 0, 3, 0, negative 1, 0, 3. There's a good chance this may get big in a hurry. Think about 3 to the 6th. 3 to the 2nd, 9 times 3, 27 times 3, 81 times 3, 243 times 3, 729-ish or something, I believe. All right, let's see what happens here. We're going to put in 3. I get 2 times 3, 6, and 0. Times 3, 18, 21. Times 3, 63, and 0. Whoop, and 0 is 63. Times 3, that's 189. That is 188. Now, times 3, we want to do this one in our head. Let me tell you what I'm thinking if I have to do this in my head. First, I wish I had a calculator. But second, what's 200 times 3? 200 times 3 is 600. But I'm 12 short of 200 times 3. Subtract 36. I've got 564. 564 times 3. I'm going to cheat and go to calculator at this point. So we've got, shouldn't have to, but as soon as I grab my calculator here, we've got 564 times. Now, as soon as I'm going to calculate, I'm thinking to myself, man, this might not be the best problem to do this way. 1692, add 3, I get 1695, and that is what G of 3 should be if I didn't make an error in that process. Okay, now, where we're really probably going to specialize in synthetic division is verify the given factors of a function, find the remaining factors. So here's my supposition. Maybe x plus 2 is a factor. And this basically says it is because it says verify that it is. How do I verify? 8, negative 14, negative 71 sounds terrible, negative 10, 24. One thing I could do is long divide x plus 2 through this. But if I synthetically divide negative 2, my box through this, I'm wondering if I can end up with 0. Then it would work out evenly. So I'm going to synthetically divide negative 2. Let's see. I get 8, and I get times negative 2, negative 16. Add them. Negative 30. Multiply. I get positive 60. Add them. Negative 11. Multiply. 22. Add them. 12. Multiply. Negative 24. Yay. So x plus 2 is verified. I'm going to then take this solution, because if this is a factor and then this is a factor, I'm going to just continue on down this road. I'm going to run positive 4, my new my box, through this. 8, 32, see where it's coming from. 2, 8, negative 3, negative 12, yay. 0. So here's what I know. I know that right now I could factor this down into x plus 2 times x minus 4 times, here it is, I went from x to the 4th to x to the 3rd to x squared. Right now I'm down to 8x squared plus 2x minus 3. And now, find the remaining factors. Well, maybe this factors of negative 24 that add up to be positive 2. That is positive 6, negative 4. If I put those guys on 8, reduce them, I get 3/4, negative 1/2. So my factors are x plus 2, x minus 4, 4x plus 3, and 2x minus 1. And if I superfoiled that out, I would get to there. Pretty slick. So list all of the real zeros. If I set this equal to 0, subtract 2, add 4, whoops, comma, forget that, 4. Subtract 3, divide 4, add 1, divide 2. There are my zeros. I'm not sure why this says Fn. This should say f of x. Just noticed that. Use the rational zero test. Okay, rational zero test is another topic that's hit on in Algebra 2, but I think maybe hearing it here first might help you, because I'm going to explain why it is rather than just what it is. So let's say for just a second, and we know what a rational number is. A rational number is a number that can be written as a fraction with integers. So 7/3 is a rational number. So what's not rational are numbers like square root of 3 or pi or e or 5i, where I is an imaginary number. Integers only. So let's say for a second, this is 5th degree. Let's say that we could get that completely factored into 5 linear factors. What do we mean by linear? Just a single x. So this would be something times x, and something times x, and something times x, and something times x, and something times x. And then this number here, and this number, so we'd have all these binomials, and when we super duper foiled, we'd get this. Well, let's consider any one of those factors for a second. Whatever is being multiplied by x, see, this times this times this times this times this equals 4, which means each one of these would have to be a factor of 4. So this is a factor of 4 times x, either plus or minus, it doesn't matter, a factor of, see, this times this times this times this times this has to equal negative 2. These have to be factors of 2 or negative 2. They share the same factors. So if I was to set that equal to 0 and solve for x, look what I would get. X is, I would be either adding or subtracting the factors of 2, and then I would be dividing by the factors of 4. Adding or subtracting the factors of 2, dividing by the factors of 4. So what are my factors of 2? Plus or minus 1 divides in, plus or minus 2 divides in. What are my factors of 4? Plus or minus 1, plus or minus 2, plus or minus 4. So all of my possible rational zeros, ones I can get from nice clean factors, would be any combination of one of these 4 numbers on one of these 6 numbers. So our possible rational zeros are plus or minus 1 on plus or minus 1, which is just plus or minus 1, plus or minus 1 on 2, plus or minus 1 on 4, plus or minus 2 on 1, plus or minus 2 over 1, plus or minus 2 on 2, but that's 1, plus or minus 2 on 4, but that's a half. There they are. So I have these 8 numbers. Any one of those may lead to, for instance, x plus 1 might be a factor. X minus 1 might be a factor. Negative 2x plus 1 might be a factor. Negative 4x plus 1 might be a factor. X minus 2, x plus 2 might be a factor. might be a zero. These are the values that might be zeros. And then I might start the synthetic process with those to see which actually are. Now, maybe none of them are, and you might say, well, that seems weird, because to the fifth goes up at the end, to the right, down to the left. So it has to, it may wiggle around, but it has to at least cross somewhere. Wouldn't that zero be there? Not if it's irrational. So this might not even find us the zeros. These are the things we used to have to do to go through to find the zeros before our graphing calculators. And you're going to say, well, why don't we just use our graphing calculators? We're going to use it, but we're going to compromise. I'm just not quite there yet where I'm ready to let this go. All right, so find all the real zeros of the function. So here's the deal, how we're going to handle this. If I'm going to find all the zeros, I'm going to set it equal to 0. I might ask for all the possible rational zeros. And again, you can memorize the rule that we just went through, or make up your own rule and memorize it. But here's what I would say. If I had a linear factor, it would be a factor of 4x plus or minus a factor of 90. If I set that equal to 0, then x is a factor of 90 on a factor of 4. And I might ask for all the factors of 90. Yikes. Factors of 90. Plus or minus 1. Let's just assume plus or minus always. 2. Plus or minus 3. Does 4 go into 90? No, but 5 does. Plus or minus 5. Plus or minus 6. 7 doesn't. 8 doesn't. Plus or minus 9. Plus or minus 10. Plus or minus 6 goes in 15 times. 5 goes in 18 times. 3 goes in 30 times. 2 goes in 45 times, and plus or minus 90. Yikes. How about factors of 4? Plus or minus 1, plus or minus 2, plus or minus 4. So in graphing calculator days, we had to do this. Try 1 over 1, try 1 over 2, try 1 over 4, try 2 over 1, try 5 over negative 1, try 6, until we found a couple of zeros. And maybe there weren't any. And now you guys have calculators, and it's not that I'm bitter, but I'm just not ready to let go of this. But I might ask you for the possible factors, and you list those out. This is kind of extreme, but you can imagine, I mean, you should go home tonight and kiss your calculator. Here's what we're going to do with this. I'm going to graph this, and I'm going to find rational zeros. So let's take a look at this as I zoom in here just a bit. Y equals, let's clear this guy out. Let's zoom so we can get a little bit better focused here. That looks good. We'll clear this guy. And now I'm going to enter my function. So we've got 4x to the 4th. Bump it over. Minus 43x to the 3rd. Bump it over. Minus 9x. Ooh, let's go back here because this is just a squared. Minus 9x plus 90. And I'm going to zoom. I'm just going to graph that in zoom standard. I'm going to go zoom standard is 6, zoom 6. Okay, so I see some zeros here. In fact, I see 4 zeros here, and that's good news. And I still have another function graphing because let's see why that is. Why? Oh, I thought I cleared that one. Let's graph that again. So here they are. And I'm going to just say, it appears as though there's a 0 at 3. So I'm going to go second calc, just value, and I'm just going to enter 3. And 3 is a 0, which means, back to here, back to zoom out. Nope, zoom back out. Maybe turn my brightening down just a little bit here. Which means that 3 should synthetically divide it. Remember, we had this. 3 should synthetically divide this. So I'm going to go 4. I've got a whole to the 3rd, 0. Don't forget that. I've got a negative 43. I've got a negative 9. I've got a 90. And now put yourself in my place years and years ago. I got to guess which of these might work, and I'm going to say, well, I'm going to guess 3 might work. Are we really guessing that 3 might work at this point? My calculator says 3 is going to work. Let's take a look. 4 and 12 and 12 and 36 and -7 and -21 and -30 times 3, -90 and 0. Woo, did I get lucky? No, I didn't get lucky. I cheated. Didn't get to cheat on them. I had to go through and just start trying, and the person next to you would be done, and they must have guessed right first, and you didn't guess right to your 15th guess. What else looks like it might be 1? Well, maybe this is 1.5, but it looks like maybe -2. I'm going to try -2's value. Oh, -2 works. So I'm going to continue from there with -2. -2, I get 4 and -8, and I get 4 and -8, and I get -15, and I get +30. Holy smokes, it worked. And I'm going to continue doing that as long as I've got rational zeros or until I get down to a quadratic. This was x to the 4th, x to the 3rd, x squared. So now I've got 4x squared plus 4x minus 15, and I'm going to see if that guy factors. Are there factors of -60 that add up to be +4? There are. They are 10 and -6. If I put those on 4 and reduce, I get 5 halves. Take a look. 5 halves. It's up there. There we go. 5 halves. And I get -3 halves. -3. That was one of my possibilities. Those are my other factors. So this guy factors into 5x plus 2. We're good at this by now, or should be. And 3x minus 2. So my very final answer, find all of the zeros. If I was to have this in factored form, I'd have x minus 3, right? We got that one. Times x plus 2, we got that one. Times 5x plus 2 times 3x minus 2. And if I want my zeros are x equals 3, -2, -2 on 5, and +2 on 3. So, again, thank your calculator, and be glad that you're in that it's 2015 and you're not doing this 30 years ago, because man, did you have to do a lot of searching, and there was some frustration involved there, but that's just what we knew. Again, not bitter, but here's your assignment. Good luck with that. Thank you, Mr. Hobb, for coming in and helping us out today.